Okay.
Okay, yeah, we see.
Recording in progress.
You see it? Mm-hmm.
Yes, I think if possible, can you make it full screen? Because at the moment we see, okay, yeah, perfect.
Full screen, it's full screen.
It's full screen, perfect. Yeah, we see it, it's all fine.
Mm-hmm.
Okay, I think we are really on time. We have 4 speakers for this session. And in order to give enough time for questions, I think it would be nice if we can stay within the granted time so that we have sufficient time to discuss the results and for questions. And the first speaker is Sergey Bulanov. He will talk about the electromagnetic wave interaction with subluminal, luminal, and superluminal mirrors. Sergey, you have 20 minutes. I will tell you 5 minutes before.
Yes, please show me this. Okay. Because it's difficult to...
Yeah, so you can tune the presentation. So
okay, thank you. Shall I start?
Yes, you can start.
Mm-hmm. Good afternoon, everybody. I would like to say about relativistic mirrors and interaction of light with such mirrors. And it is a recent work which has been done together with Timur Serkepov. And we have already heard about relativistic mirrors on yesterday from presentation of Dina Yaroshinsky. He mentioned about such appearing, disappearing optical objects in laser plasmas. And we are working since a long time on relativistic mirrors, of course. And with my colleagues, whose contribution I appreciate, from LPHYS'23, Kansai Photon Science Institute, Osaka University, Institute of Physics, Chinese Academy of Sciences, Gerard Moreau-Tajima. We worked with them also, and people from Berkeley and Pisa University, Francesco Pigarano. And we know well that relativistic mirrors appeared in theoretical physics thanks to Einstein as one of the problems of theoretical physics, and not only theoretical. And in his paper on special relativity in 1905, he used he solved the problem of reflection of relativistic mirror with the light in a very elegant way, illustrating basic principles of special relativity. And actually, Abraham started also to work in this direction. We should remember this. And then it was seen immediately that such mirrors can provide the conditions for frequency upshifting and intensification of the reflected light. That is why for already more than 100 years, this problem has been attracting attention of theoreticians and people who do the experiments. In laser plasma, also there is such a high level interest towards studying relativistic mirrors. And here in my presentation, I will touch some aspects of this physics. First of all, I would like to make a brief introduction to relativistic mirrors, reminding what is known well. And this process of frequency upshifting is related to double Doppler effect. And then there were efforts, theoretical studies and experimental efforts to see relativistic mirrors generated by relativistic electron beams, by ionization fronts, and many other approaches have been used. In the case of interaction of electromagnetic wave with a slab of material, for example, plasma or some other material, a portion of electromagnetic wave is reflected and portion is transmitted through, and we can find the change of the frequency of the reflected light, omega r, and depending on the velocity of the mirror and angle of incidence. And it is seen that there is enormous frequency upshifting due to relativistic effects, which is a factor of the order of 4 gamma squared. Gamma is calculated for the velocity of the mirror. the angle of reflection is not equal to the angle of incidence, the reflection, and then the amplitude of the reflected wave also increases in such a factor for gamma squared. And there are many in the laser plasma. There are several here. 6 pictures, actually, there are more pictures when we see this effect of interaction of a strong electromagnetic wave with relativistic mirror. And for example, there is an oscillating relativistic mirror as a mechanism of generation of high-order harmonics in the laser solid target interaction. Then receding mirror, when the laser radiation pressure pushes forward thin slab of plasma and reflected back. In this case, there is not frequency upshifting, but frequency downshift due to transferring of the energy of electromagnetic wave to the plasma slab. This is the efficient mechanism of the ion acceleration. Then there is a double-sided relativistic mirror. When we accelerate a thin slab of plasma by one laser pulse and then send counter-propagating laser pulse to see frequency upshifting and high-order harmonic generation, but they appear in the form of boosted form of the harmonics. Then relativistic flying mirror, when we have one slab of thin shell of electrons, for example, generated by strong linear wave, and counter-propagating laser pulse reflects from such the mirror. Then it could be another mechanism when we have not a single electron layer, but multiple layers, because due to development of the some instability or modulations of the mirror, it breaks up into the pieces. Nonetheless, this swarm of mirrors can generate frequency upshifted and intensified electromagnetic radiation. And I can remind you how it happens, basic principles of scaling, how to find the scaling of electromagnetic wave reflected from the paraboloidal mirror, which appears spontaneously due to transversal homogeneity of laser pulse or due to the structure of a wake wave, or prepared another way. In the laboratory frame, we have the incident laser pulse with given frequency, in this case omega s, and intensity is. Then in the moving with the frame, moving with the velocity of the mirror is stationary, but with different curvature. Here we have standard reflection from the paraboloidal mirror with the formation of the focus spot with a size with approximately lambda prime. Lambda prime is shorter wavelength than the incident light, but it is not shortest. And then if we reflect, make transformation back into the laboratory frame, we find that the mirror is frequency upshifted in this shortened wavelength, as I have mentioned, but the focus due to this fact that it moves with relativistic velocity is not spherical, but it has a form of disk, which is important for calculation of the scalings. And we have, you can see this interaction of the counter-propagating pulse with linear wave generated by driver pulse, and you see by naked eyes the reflected light, which has a form of frequency upshifting that the wavelength is much shorter. The intensity of the color is also higher, means that intensification, and it is focused due to because of the structure of the wake wave. And in Japan, at the Kansai Photon Science Institute, our team made experiments with counter-propagating laser pulses under dense plasma, and proof of principle experiment has been done, showing frequency upshifting to the factor approximately, I don't know, maybe even 100 times. And it is this ultraviolet, extreme ultraviolet photons appear in the form of Fox pulse, and the number of photons generated corresponds more or less to what we predicted analytically. Then we can solve many problems. There are many methods of calculation of the reflected light. It's a mirror moving with along some trajectory. And here you see oscillating mirror when the mirror oscillates back and forth, and you have reflected light in the form of attosecond pulses. It's, as I said, it's a basic mechanism of Hellner harmonic generation in the laser solid target interaction. But if you say about oscillating mirror in more details, then we should get in the theory of plasma resonance, what happens in the vicinity of critical density. Here, the modulations of the electron density, they don't have a form of oscillating back and forth mirrors, but they have a form of some driven by the laser electromagnetic field modulations of density of electrons, which propagate with a phase velocity which can be quite higher towards low density plasma. And they appear, nonlinear modulations appear as some kind of spikes, appearing, disappearing spikes, moving with relativistic velocity. This process leads to the generation of the attosecond pulses. And then we should think about reflectivity, because if we now know about frequency upshifting, it's a universal relationship. But if you are interested in observing a decent amount of the photons, high intensity, then we should calculate the reflection coefficient from such the mirrors. Apparently, it cannot be equal to 1, otherwise it would be not conservation of the energy, and it is less than 1, but what is it? We calculated several times such the coefficient, reflection coefficients, but here I would like to say about some general properties and constraints on such the reflectivity of the electromagnetic wave. And this, again, this formula is about frequency upshifting and intensification of the electromagnetic wave. Rho is reflectivity in this factor. G, it gives the frequency upshifting. For subrelativistic and superrelativistic mirrors. And you see, special relativity does not forbid to have the mirrors moving with a velocity greater than speed of light. The particles cannot move with velocity greater than speed of light, it's obviously, but the mirror can be made by the modulations of the density of electrons or some other modulation of refraction index, which moves with a phase velocity, like in the linear wave, for example. Phase velocity could be arbitrarily large. And that is why beta mirrors, normalized velocity of mirror, can be greater than unity. Here you see the results of computer simulations made by Timur and Sarkepa. In the inhomogeneous plasma, a laser pulse propagates through such a slab of plasma. And due to the inhomogeneity, there is an effect of phase mixing in the linear waves, which changes the velocity, phase velocity. And you can see clearly that the position of this high density spikes, electron spikes, depends on time and coordinate in such a way. And at some moment, even V mirror, velocity mirror minus C can be 0. It means that it reaches the velocity of speed of light. It's no contradiction with special relativity. Then when we have the interaction of the relativistic mirror with of subluminal and superluminal relativistic mirror with laser pulse, then at the mirror, for example, with subrelativistic portion of electromagnetic wave propagates through the mirror, and reflected light propagates in backward direction, and you see the simple geometrical consideration shows that there is a compression of the light. pulse. When we have super relativistic superluminal mirror, in this case, transmitted light approximately the same, but if you wish, you can say that it is reflected pulse or it is transmitted. Reflected because of it is not transmitted, but not the same, but it's hard to say that it is reflected because of it remains behind the mirror. It propagates with speed of light, but mirror propagates faster. And then if to say about the reflection coefficient in more details, as I said, we can consider a simple model for reflectivity. Let's consider the mirror which moves with velocity beta m. Its position is here, and we can consider, for simplicity, half space of plasma, which with a density, step-like density, propagating from the right to the left. We use Fresnel formula for reflection coefficient. Here is refraction index. In the plasma, it is expressed in such a form. And we see that reflection coefficient in the case when omega p over omega much less than unity expressed in such expression. But in the case when we have relativistic motion in the frame of reference moving with a mirror, subrelativistic, for example, the frequency of electromagnetic wave is higher. That is why it is in the denominator. And we see that when gamma factor tends to the infinity, beta tends to unity, then the reflection coefficient tends to 0. We have here some kind of counterplay between the factors that amplitude wants to increase or grow, but the reflectivity drops, and that is tends to 0. That's why we need to solve this problem more rigorously. We solve the wave equation, actually Klein-Gordon equation, with omega p here, which depends on time and coordinate. We are changing to such coordinates psi and eta, and the wave equation becomes of such a form with small parameter in front of higher derivatives with respect to eta. And then we can calculate the reflection coefficient for subluminal mirror using these equations, just matching solution of equations at the plasma vacuum interface. And we see that reflection coefficient really tends to 0 when beta tends to unity when it approaches speed of light. And the same is for superluminal mirror. The two transmitted waves, they are expressed here. We can find what is the phase here and the amplitudes. And when beta tends to unity, we have some kind of singular point. Let's consider reflection at luminal mirror when it moves exactly with the speed of light. Here, these equations become a wave equation takes such a form. It's easy to integrate. It's trivial to do this, but it's I like this expression. It has a form of change of phase of the wave, which depends on coordinates and the frequency of incident wave. And immediately we find that there is a frequency upshift in such a factor omega pe with the second power over omega incident light. We can find a phase and group velocity of the laser pulse, of the electromagnetic pulse interacting with such relativistic media. And depending on the initial frequency of the light and the molecular frequency, the wave can propagate towards positive direction or negative direction, but it doesn't overtake the front of the pulse because of it is moves with velocity equals to c. Here, there is a solution of these equations, wave equations. You see that mirror is here, laser pulse is incident on the mirror, relativistic mirror, which moves with the speed of light behind. We have such a wave pattern, and we have such the effect due to it interacts with the light interacts with the plasma, and here there is also dispersion effects which we should take into account. We can find how the phase depends on coordinates. Actually, it is expressed in terms of Bessel functions. I don't want to take your time to say about the Bessel functions. And it is seen as this numerical solution of this equation. Mirror moves to the left, laser pulse propagates through the front. It is modulated due to the dispersion effects and relativistic effects. In the summary, it's the main conclusion of what comes out from this consideration. We have upper limit of the frequency upshifting. And it is quite universal. I consider it semi-infinite plasma, but actually it is for slabs, finite slabs in the various profiles is the same. And here reflected light frequency is related to the frequency of incident maximum possible frequency of shifting. And it is depends on the frequency of incident light and the plasma frequency of the medium which moves towards this pulse. And then we can calculate intensification of the light due to longitudinal compression. And then we can calculate, I didn't consider here non-one-dimensional geometry, but actually we know what happens there. We need to consider the focusing into the focus spot, which is determined by upshifted frequency. And we have such a scaling, which is quite good and quite optimistic, that we can increase, for example, if a critical density of electrons is 10 times or 100 times higher than critical density, which is possible. And in this case, we can have intensification of many orders of magnitude and approach Schwinger field, as we claim it in our first paper on the mirrors together with Isir Kepler, Timur, and Torstad Jina. And it's the end of my presentation. And here you see Japanese calligraphy, where it is written a relativistic flying mirror. Thank you for listening to me.
Thank you very much, Sergei, for a very nice talk. It's now time for questions. So if you have questions from the audience, you can just unmute you or raise your hand. So at the moment, I see no questions. So perhaps I start with one question. So my question is actually, if you can go back one slide. Yeah, it's very much related to what you write here, this spatial recoil geometry, other effects. So this mirror is probably strongly affected by the oncoming laser pulse, right? And this will change things. So probably it will be dispersed, we'll get some momentum kickback. So how things change when you consider the effect of the laser that is reflected?
Yes, you're absolutely right. It's a very serious question. I said the effects, it's an upper limit. Here I write most optimistic upper limit, but nonetheless it's finite. It's not, how to say it, infinity when beta tends to unity. And then the dispersion effects, they broaden the mirror. That is why, not mirror, but electromagnetic waves. That is why compression to the small spot and to small vision is not so easy. Recoil effect. Also, it is important to take into account, and we work on the recoil effects, and Petr Valenta from our team works actively in this direction. Geometry, how it is, we consider usually idealized mirror, idealized laser pulse, but when we have various inhomogeneities, not always there will be, the effect will be positive. But here, maybe the most interesting effect is recoil effect, back reflection, because we here considered linear approximation with respect to the amplitude of electromagnetic wave. But what is recoil effect? Of course, it is important. It is important, and it decreases the efficiency of this process. But it is wise to make white laser pulse, a white laser pulse, to decrease its intensity on the mirror. And the reflected light, then it is compressed in longitudinal direction and in transverse direction. I can say this compression in the longitudinal direction has been seen already by Einstein and repeated reproduced in many other theoretical works. But in our paper with Timur Sirkepov and Tosh Tajimov, for the first time, we said that we need to consider transverse compression intensification of the laser pulse. And this idea has been rediscovered many times after us. That's why we don't need to. We can actually try to weaken this effect of the recoil.
Okay, thank you very much. There is one question from Henry Vincenti. Please go ahead.
Yes, so hi Sergey, thanks for the nice talk. So I had two questions. So the first one is, you assumed a perfectly parabolic mirror, right, without any aberrations. So what is happening when you take into account like realistic laser parameters, and what is the minimum wavelength you need to focus in your scheme to achieve the intensity gains you mentioned?
You see, you see. Of course, you are right that reality is less perfect than less idealized than we do when we play with in the theory. And in reality, we have various modulations of which appear, for example, due to the laser pulse radiation pressure or some other effects on the development of instabilities on the mirrors. Sometimes they play a positive effect. For example, recently we already start to publish the paper with self-modulation of the mirror and generate new mechanism of high-order harmonic generation. This self-modulation is not always negative. But we should be careful. That's why we made it with red color, this effects. It's geometry and etc. It's self-modulation. So of course they can make it, we don't control them, they can destroy these effects. You're right. But what is practically we should have? This I'm not sure that I can answer not immediately on this on your question, but we published several papers saying about more or less realistic parameters for the laser pulse wavelengths, the intensity, power, duration of laser pulse. For example, Taimur John, who is here, and he will present his talk. We published I don't know, 1 or 2 years ago paper when the paper when we made maybe the most accurate estimations of these effects.
Okay. I think we need to move to the next seminar and talk, because we are already 7 minutes beyond schedule. So thank you very much, Sergey, for the very nice talk.
Stop share.
Yes, can you please?
Okay, thank you.
Henry Vincenti, can you share the screen?
Yes. Yes. Can you see my screen?
I can see. Okay, perfect. So it's full screen. So the next speaker is Henry Vincenti for CSA Clay. He will talk about plasma mirrors, a path to compact particle accelerators, and extreme intensity light sources. So you have 30 minutes. After 25, I will show you that you have 5 minutes left. Okay? Thank you very much.
25 minutes. Okay, so first I would like to thank the organizer for the nice invitation. And today I will discuss about relativistic plasma mirrors, which are remarkable optical components that we are trying to use to solve two major challenges of high field science that I will briefly present in the context of my presentation. So the first challenge is the following. So can we probe the strong field and fully non-perturbative regime of quantum electrodynamics that arise in light-matter interactions when the so-called chi parameter, which is, for instance, for electrons, the field seen by the background field seen by electrons in their rest frame. So when this parameter becomes much larger than unity, so this means that the field seen by electrons in their rest frame is much larger than the so-called Schwinger field of 10 to the 18 volt per meter. So this is huge. And why is this important to probe this regime? So the first thing is that the strong field regime, although theory has been developed in the 1970s and up until now, it has been barely explored in experiments. So it is terra incognita from experiments. And it is very important to validate the theoretical models at chi much larger than unity models that have been developed in the literature. So this is the first thing. So the second thing is that reaching the fully non-perturbative regime, when the which is conjectured to occur when alpha chi to the 2/3 is larger than unity, which corresponds to chi larger than 1600. There is no universal accepted theory, and accessing these regimes experimentally is really important to guide theoretical developments in this regime. So what are the limitations? So obviously, reaching the field comparable to the Schwinger field will require a very intense light source. So this has been the major impediment so far to reach those regimes. So if we look at what have been achieved, for instance, the most famous experiments is the so-called E144 experiment that was performed at SLAC in the 1994, where they collided a 46 GeV electron beam with a terawatt class laser, and they could achieve, in this particular configuration, a chi parameter of around 0.3. You have several planned experiments, some in Europe, some in the US, still on the collision configuration. For instance, the LUXI-B experiments are planned to collide the electron beam for the European XFEL with a 350 terawatt laser, where they plan to achieve a chi parameter of around 4. And the E320 experiment at SLAC, where they plan to achieve a chi of the order of unity. So these chi parameters are the order of unity, and so there is a huge gap to explore between this chi parameter and the so-called fully non-perturbative regime. And the question is, how do we access this range of chi parameters? So this I will discuss in my presentation. This is the first challenge. The second challenge is, can we develop high charge, high quality GeV class laser plasma particle accelerators? So the most famous of laser plasma accelerators is the laser Wakefield accelerators that can be obtained by focusing a high power laser into a gas jet. In this, you generate a plasma structure, a bubble that can hold a really huge electrostatic field of around 100 gigavolt per meter, and that can accelerate electrons so you can have electrons trapped in this structure and accelerated to relativistic energies over centimeter scale. So there have been considerable progress done in the past 20 years. So from the initial 100 MeV electron beam demonstration in 2004 by several groups, up to the present record of 8 GeV at Berkeley on a centimeter scale accelerator. So these accelerators are very promising to build cheaper and more compact accelerators, but they currently suffer from an important limitation, which is the low amount of charge that you can get at high energy, so at multi-GeV energies. And the reason for this is that conventional injection techniques, so to inject electrons into the accelerating structure, rely on the injection from the gas medium, which is a relatively low density. And unfortunately, going to high energy, if you look at the scaling law, it requires decreasing the gas density to increase the dephasing length of the accelerator. And so if you decrease density, you basically decrease the amount of charge you can inject in a short time. And you need to inject charge in a short time so that each electron of the packet is accelerated over the same length. So you get a high beam quality. And so it's really difficult to increase the charge and go to high energy while keeping a high beam quality. So this is the second challenge we try to address. And so in the following, I will show you that these two challenges that look totally different can actually be addressed by a common solution. So a remarkable physical system called a plasma mirror that I will now detail. So a plasma mirror can be obtained by focusing a high power femtosecond laser with a high contrast, sketch here, on an initially plain and solid target. That is sketched in gray. And so at laser focus, the laser field is so intense that it completely ionizes the target and creates a dense plasma that barely expands during the interaction owing to the high laser contrast and the small laser perduration. And this plasma expansion generates what we call a gradient scale length, which is much smaller than the incident wavelength of the laser, which is a key parameter of the to control the interaction. And as the gradient scale length is much smaller than the incident laser wavelength, so the solid density plasma will act as an optical mirror of excellent quality, a so-called plasma mirror, that can specularly reflect the incident light. And upon reflection, so the incident laser field can drive relativistic oscillations of the plasma mirror surface, so hence generating a so-called relativistic oscillating mirror, as you can see here on the bottom left, which is a simulation movie of the plasma electron density. So you can see the driving laser field driving a relativistic oscillation of the plasma surface. And this temporal oscillation can periodically compress and distort the reflected field, as you can see here on the upper right. And this periodic distortion is associated to a Doppler high harmonic spectrum, the frequency domains that has been measured and controlled in experiments. And so this periodic compression leads to a first intensification by Doppler effect. And actually, we recently demonstrated that the natural curvature of the plasma mirror surface under incident laser radiation pressures that you can see on the movie can lead to a focusing of the reflected field that you can see on the second simulation movie on the bottom left. And the combination of the temporal compression and the spatial compression we demonstrated in a very challenging plasma simulation that we can reach orders of magnitude intensity gain. So plasma mirrors could offer the possibility to Doppler boost existing high power laser to an unprecedented level of intensity. So another very nice feature of these plasma mirrors is that the incident laser field can eject electrons coming from the plasma mirror surface and accelerate them in the reflected light. So this had been demonstrated in experiments and modeled in simulation and theory by our collaboration between our group and LOA in 2016. So you can see here on the bottom left results from simulation where the incident laser field can eject electrons from the plasma mirror surface, inject those electrons in the reflected field at very precise location. And these electrons, as you can see on the right here, then undergo vacuum laser acceleration over typically a laser relay range. So this is nice, as we demonstrated in experiments, that it can provide sub-femtosecond up to 10 nanocoulomb charge, so very high charge, but at small energy, so MeV. So this offers the nice prospect of using these plasma mirrors as high charge, high precision injectors. And we will see that we could use these injectors in a laser plasma accelerator, in the laser wave field accelerator. So this brings me to the outline of the talk. So in the first part, I will discuss the prospect of using plasma mirrors as a high charge, high precision injector in a laser wave field accelerator. In the second part, I will show you how we could use Doppler boosted lasers to reach strong field and non-perturbative regimes of QED with existing laser facilities. And finally, I will conclude. So let's jump to the first part. So laser wave field accelerators that I previously introduced have very nice features. So they can already achieve high energy, multi-GV, low energy spread, a few percent, small divergence, a few millirad, and but they typically offer low charge, especially at high energy, so below tens of picocoulombs at GV and above. So this is not enough. We want to scale this charge up to nanocoulomb. And on the other side, you have vacuum laser acceleration that I previously introduced with plasma mirror injectors that can offer very high charge. So this is nice, up to 10 nanocoulomb, but low energy, high energy spread, and high divergence. So this is not suitable for applications of this beam. So as you can see, what will be nice is to have a combination of both worlds and to achieve high energy and high beam quality. And to achieve this, we recently proposed a novel concept, which we dubbed hybrid gas and solid targets that are sketched here. So the principle is really simple. So you focus a high power laser onto this target. First, it will interact with the plasma mirror, and the plasma mirror offers orders of magnitude more charge density than the gas medium. And so you will eject high charge sub-femtosecond electron bunches from the plasma mirror. And after reflection of the laser, these electrons will be trapped in the wake field created by the reflected laser in the gas part. And this has been sketched here. So these are results from 3D simulations we performed on the Summit supercomputer in the US. So you can see here on the left, the laser in blue color and red, and the plasma slab on the bottom. So you can see that after reflecting on the plasma slab, the plasma mirror, you can see here electrons from the plasma mirror surface that gets nicely trapped in the wake generated by the reflected laser field in the gas part. So when we had this idea of the concept, so the first thing we needed to do is to validate this concept in a very challenging simulation. So simulations are key to understand the basic physics of the injection into by the plasma mirror into the wake field, but also design, guide, and interpret experiments that were done at Laboratoire d'Optique Appliquée by our collaborator Adrien Leblanc. And there was a huge numerical difficulty in doing this first proof of principle simulation, is that we need a 3D description to get the charge and the quantitative properties of the injected and accelerated electron beam. And this required a 3D kinetic description on huge spatio-temporal ranges, so from 10 to the minus 8 meter to 10 to the minus 3 meter. So from the scale of the plasma mirror surface up to millimeter scale acceleration in the gas part, and from a sub-femtosecond to a picosecond time duration. So this is huge and was not possible with standard tools before. So to overcome this challenge, we developed the WARPEX particle in cell code, which can catch kinetic effects in light plasma interaction. And this code relies on the base peak method. So where you solve Maxwell's equation, you could self-consistently solve Maxwell's equation on a grid, and the relativistic motion equation of plasma particles that can move freely through the grid, and field and particle interact through interpolation assignation between particle and the grid. So WARPEX, thanks to developments by notably by Berkeley collaborators and our group at CEA, so WARPEX now supports many advanced features. Some of these features are unique and were co-developed by my team and Berkeley, and the team of Jean-Luc Vert at Berkeley. So WARPEX now include mesh refinement capabilities that are crucial to handle the huge difference of time and length scales in the simulation. Pseudospectral Maxwell solvers, especially for Doppler boosted beam. For plasma acceleration, boosted frame transform, and you can also have physics beyond Vlasov, such as QED processes that we use to get the signatures you can obtain by interacting Doppler boosted beam with a solid target, for instance. So these are all the features you can find now in WARPEX. So WARPEX, as I mentioned, is developed by a multidisciplinary, multi-institution team. So it is primarily developed by Berkeley Lab through the Exascale computing project. So the PI there is Jean-Luc Vert, our main collaborator. And at CEA, we have been a core developer of WARPEX since its beginning on the optimization of the code, on the development of new numerical methods, especially tailored to our physical applications, so plasma mirrors and laser plasma accelerators. So thanks to our optimization, we could scale the WARPEX code on the largest supercomputers worldwide. So we scale the code on the top 3 supercomputers, and including the first exascale supercomputer Frontier in the US. And we did this scaling with mesh refinement capabilities that enabled a 4x speed up on the simulation of the hybrid target. And thanks to all this optimization, we could perform the first simulation of the in 3D of the hybrid target. So this simulation is sketched on this little movie on the right, where you can see again. So the laser that is impinging on the solid slab, and after reflection, so you will see here, after reflection, electrons from the plasma slab gets captured in the bubble behind the main laser and gets accelerated over a millimeter to centimeter range. And you can trap a lot of charge. So thanks to these developments, this first physical demonstration, We obtained the Gordon Bell Prize in 2022, which is the highest recognition in high performance computing. And this prize were awarded to a collaboration gathering CA, Berkeley Lab, and industrial partners such as Gency, ARM, and Atos. So the exascale simulation we performed informed us on the design of the first experimental validation of the concept that I presented at Laboratoire d'Optique Appliquée by our collaborator Adrien Leblanc. So we could understand which laser polarization is best to optimize electron beam properties, which gradient scale lamp to use on the plasma mirror to optimize the beam properties. And here you can see the first shots that were obtained at LOA with this hybrid target. And we get a very nice electron beam with a high beam quality and a fourth increase in laser to electron yield compared to previous techniques. So, for instance, we compared the results for this first experiment that were obtained with a 20 terawatts. So we obtained 80 picocoulomb in the main peak at 300 MeV with below 10% energy spread. And this, our simulation were in very good agreement with the first experimental results in terms of peak energy, total charge, and the energy spread. And using our simulation, we predicted the scaling laws with laser power, and we predict up to nanocoulomb charge with percent level energy spread with a petawatt class laser, which will be a huge milestone if we could achieve this in experiments. So there is an experiment plan at petawatt based on this design. So now we'll switch to the second challenge, the second part of my talk, which is how could we reach strong field and non-perturbative QED regime with Doppler boosted beams. So actually, with Doppler boosted beam, we assessed what is the intensity we could reach using different focusing techniques for the Doppler boosted beam and as a function of laser power. So this has been summarized in this plot, where you can see on the black curve the intensity you could get at focus of plasma mirror, which is naturally curved by the incident radiation pressure. So you have nothing to do. So the focusing is provided by the intrinsic curvature of the plasma mirror. And you can reach already intensity between 10 to the 25 to 10 to the 26 watt per square centimeter with a petawatt to multi-petawatt laser. So this is an intensification of more than 3 orders of magnitude. And achieving this in experiment would already be a major milestone at petawatt level. And the red curve is the upper limit you can get. So if you imagine you could focus the harmonic beam down to their diffraction limit. So this is an ideal limit. But in between, we have good strategies to fill the gap and increase the focusing compared to a radiation pressure. So you have all optical techniques that we explored, and you could also imagine relying on external refocusing using an external XUV optics. And so you could explore a range of intensification between 10 to the 20 to the 3 up to 10 to the 6. And this makes accessible the Schwinger limit, the Schwinger intensity limit of around 10 to the 29 watt per square centimeter in the lab with the existing petawatt laser. So this is obviously very challenging to reach the Schwinger limit, but we could expect already really nice intensification factors with state-of-the-art lasers. So to explore, to reach strong field and non-perturbative QED regimes in the lab and measure the QED signatures of this regime, we plan to implement 2 configurations in the experiment that we simulated, and I will present the simulation results in the following. So the first configuration is to rely on the natural curvature, for instance, of the plasma mirror. And as you can see here, focus the laser on an initial, on the lower arm of an L-shaped target to generate a relativistic plasma mirror that is curved. And this curvature will focus the Doppler boosted light on an upper arm, this sketch here, to trigger strong field QED processes. And this is not science fiction, so this kind of targets can be engineered with a really nice optical quality. So this is a prototype that was done by Professor Ercomer's group with 3D microprinting for us. So this configuration is optimal to trigger a prolific QED signal to check that we entered the strong field QED region. So this will be a first milestone, but also to study strong field QED per plasmas. So we expect relativistic electron-positron plasma jets where plasma effects could play a role. The second configuration will be to collide a relativistic electron beam of multi-GeV produced by a laser plasma accelerator with a Doppler-boosted petawatt laser to reach a very high chi parameters. And this will also be a nice configuration to isolate a strong field QED signal from plasma signal. So this could also, so this would be nice to have an accurate validation of the strong field QED theory, but also explore non-perturbative, access the non-perturbative QED, fully non-perturbative QED region. So I wanted to position this configuration and especially configuration 2 regarding the current planned experiments and the state of the art. So this plot was taken from Advances in QED that was published in 2022, where there is you can see the positioning of the different experiments in the Xi, so which is normalized laser amplitude, and the eta parameter, which is chi over Xi parameter. So isochi lines, you can see isochi lines on this plot, and you can see that the configuration 2 is we can explore a parameter space which is inaccessible from state-of-the-art techniques and other planned experiments. And ideally, with a multi-GeV beam and a multi-petawatt laser, we could approach the fully non-perturbative regime in experiment if this scheme is successfully implemented. So now we'll detail the signatures we could expect from these two configurations. So we performed challenging simulations, peak QED simulations with our WarpX code. So we simulated the first configuration where you generate a plasma mirror on the lower arm of the L-shaped target, and you focus the Doppler boosted light on the upper arm to trigger strong field QED processes. So you have a gamma photon production by quantum synchrotron and the decay of gamma photon in the strong field into an electron-positron pair, so the so-called nonlinear Breit-Wheeler effect. And so we simulated, for instance, the interaction of a tightly focused 4 petawatt Doppler boosted laser with the secondary solid target. And what we observed is that the Doppler boosted light penetrates into the solid density due to relativistic transparency, but also the short wavelength of the Doppler boosted component. And in this plasma, it triggers prolific electron-positron pair production. So this electron-positron pair gets accelerated from the electrostatic field in the plasma channel created in the dense target, and also the Doppler-boosted light field. And you can reach a multi-GeV energy here, you can see on positrons, and also a multi-GeV gamma photon production. So you can produce ultra-dense and multi-GeV electron-positron pair jets. And if you look at density, you can see you can reach 1,000 times on this plot on the color scale the solid density for positron beam. So which is the highest density you could get in the laboratory with Doppler boosted beam compared to other techniques. And we also simulated the second configuration. So here I plotted a movie. So here on you can see the Doppler boosted light in blue and red colliding with a relativistic electron beam, 10 GeV electron beam, crossing the Doppler boosted light at an angle. So we choose an angle so that the electron mainly interact with the high field region to get the highest chi possible. So if you have head-on collision, you lose a lot of energy in the first cycle of the Doppler boosted light, and so you reduce the overall chi parameter you can achieve. So, and so here I will play the movie. So you can see that when the electron beam will cross the Doppler boosted light, okay, I'm almost done. It will trigger gamma photon production in orange, so you can see gamma photons, but also electron-positron pair in purple and green. And you can see that this electron-positron pair we play again the movie, once they are produced, most of them get strongly accelerated by vacuum laser acceleration, so into the Doppler boosted light. And this leads to a production of a bright positron beam and also bright gamma rays. So gamma rays are mainly produced in the direction of the incoming electron beam. At multi-GeV, so this could be easily measurable signature in the experiment. So if I summarize the results we recently got in the simulation, so the Doppler boosted beam interaction in the two configurations could allow to achieve unprecedented pair densities in the laboratory. So with plasma effects, relativistic electron-positron pair jets with plasma effects that are relevant to many transverse research fields such as astrophysics. So these pair plasmas are pervasive in close to compact astrophysical objects. So second feature is that we get a huge Doppler boosted laser depletion, especially in interaction with the solid target. So we get up to 80% laser absorption into gamma photons. And the laser is almost completely depleted into pairs and gamma photons. And also the second configuration offers the prospect to reach unprecedented chi values. So here you can see the chi values you could reach as a function of the focus intensity and with a 10 GeV electron beam. So you can see you could already access or being close to the fully non-perturbative regime even at 10 to the 26 watt per square centimeter intensity. So now I conclude. So I would like to highlight two messages. The first message is that plasma mirrors, we demonstrated in simulation and experiments that plasma mirror can act as high quality, high charge injectors to level up the charge by laser wave field accelerators, especially at high energy while keeping a high beam quality. And the second message is that plasma mirrors can act as intensity boosters to reach strong field and fully non-perturbative QED regime with existing laser technology. So this is not science fiction. All the concepts I presented have been at least validated in the 100 terawatt regime with Doppler boosted beam. So we measure the spatial quality, spatial wavefront, and temporal compression of the Doppler boosted light at 100 terawatt, and we compare this to these models. There is a good agreement. So the main challenge will be now to scale this experiment to the petawatt regime. There are some challenges, but there is no reason we should not be able to overcome these challenges. And we will try to, once the Doppler boosted light is controlled in the petawatt regime, we will try to implement configuration 1 and 2 in experiments. And the second challenge will be to demonstrate the hybrid solid gas target at the petawatt level. So there is an experiment plan at Apollon Laser Facilities by Adrien Leblanc, our collaborator Adrien Leblanc at LPHYS. So thanks for your attention, and I'm ready for questions if you have questions.
Thank you very much. Thank you very much. Very nice talk, very rich physics. It's now time for questions. I think I will start. I actually have 3 questions. So the first question is, how much of the initial laser energy can you deposit on the reflected and focused laser, right? So you have your petawatt laser incoming, and then it's reflected and from the mirror and it's focused. But at the end, how much energy you deposit on target of this? And the second question is, on which volume? So how much energy on which volume? I have another question that I keep for later.
Okay, so that's a good question. So in the simulation we perform, we measure this, and for moderate gradient scale length, so typically the optimal scale length we use is lambda over 10. And the p-polarized lasers that you need to get the Doppler boosted light, you get an efficiency, so the incident laser energy into harmonics of around between 70 and 80%. So this is huge, and actually you get a significant, so you get almost 20% of the reflected energy into high order harmonics. So from our harmonic order 2 to the cutoff, which is around 50 or 60. And then regarding so this is huge. This needs to be measured, but it's complicated because in experiment you need a diode and you have many noise, and it's really difficult to isolate the Doppler boosted light from the noise in the experiment. So This will have to be confirmed in experiment by assessing the peak intensity you get at focus, either indirectly, measuring signatures or so on. But actually, from simulation, which are first principle, we have good confidence. We expect a high conversion efficiency. And for the focal volume, then it depends on how you focus your Doppler boosted light. So if you rely on radiation pressure focusing, for instance, you have a transverse spot size of 0.3 micron, typically. So if you start with a laser spot size on target, which is 4 micron, and if you increase the focusing, then you can get to a transverse spot size of tens of nanometers, typically. So this will depend. But a nice result is that what we observe is that as we are below the threshold of strong field processes, the increase in peak field amplitude you get from the boosting largely compensates the decrease of the interaction volume. So this does not hold as when you cross the threshold of, but with existing lasers we are below this threshold. So this is why we gain with the Doppler boosted light.
Okay, so, just another question, and then does the material play any role of the mirror? And the second question is, for your simulations, did you benchmark this code workbacks with something else, or did you find that GPUs give a big performance boost? And that's it from my side.
Yeah, so the performance boost we obtained from GPU are way above the one we could get from CPUs. We did many development on, especially on ARM processors, thanks to our industrial partners. So we did significant work to improve vectorization of the code on the CPU. But overall, the GPU code has a better performance. You had a first question, but I forgot.
The material of the mirror.
Yeah, so the material, so I would say it doesn't make a big difference, but if you can use a material that you can cut very precisely, for instance, along a crystal direction, you could achieve a planarity, which is where you could basically decrease target imperfection that you will get in experiment. Let's say, but when we measured in the case of the experiments at 100 terawatt, when we measured the spatial temporal profile of the reflected light, we didn't see any effect of this potential imperfection on the quality of the phase front, spatial phase front of the beam. So I would say we will have to see at petawatt level. I guess I cannot answer for sure.
Okay, thank you very much. There is one question there is a question from Laszlo. Please go ahead.
Thank you. Really interesting results. Congratulations, Henry. Comment and a question. A short comment that nowadays, I agree with you that the charge from laser wake field accelerators are typically low. However, with injection, like shock front injection at MPQ, Munich, they managed to, in cooperation, we managed to reach with about 100 terawatt laser already more than 100 picocoulomb, and petawatt scale, still sub-petawatt laser already nanocoulomb. So that is with high quality.
Yeah, I agree with you, but I just have one remark about this. So I saw the results and it's impressive. But if you look at results above GV, then I cannot find a single result, but maybe I'm wrong, but
No, that is true. It's a few hundred MeV, I think, above.
Yeah. And that's the issue, is that if you want to go above GV, I agree that conventional injection techniques, they produce very huge beam quality in the 100 MeV range, and you can get a lot of charge. Basically, if you scale energy, so you go to petawatts, so you can get above nanocoulomb charge in the beam, but it's at 100 MeV. And if you want to go to above GV, then inevitably you will have to reduce the density of your gas medium. And if you rely on shock injection, you will also decrease the amount of charge you can inject. And when we look at literature and all the experiments that have been performed at GV, the charge is below 10 picocoulomb, basically. I don't say that it won't be possible to achieve a higher charge with conventional injection technique, but I guess it will be difficult due to this.
I bet it will be possible based on that. These former results, they are below GeV, but not much. But no, the question, you showed very shortly the results with this, I call this a plasma mirror injector. Could you comment on the comparison between the laser weak field electrons? Like you didn't show divergence, you mentioned the charge was 4 times higher. I don't know, electron spectrum is how does it perform?
Yeah, so these are the preliminary data that have been, so the data are still being analyzed. So the paper is not out yet, so I selected, these are the data selected by my colleague and that is sent to me. So basically in terms of divergence, so in terms of energy, so we compared to the energies that was done, the experiment that was done by Jérôme Faure at LOA with a similar energy. And with the same laser and at given energy, we got four times more charge, typically at 300 MeV. So this is the basis of comparison. And regarding the divergence, we typically are below 10 millirad. So I didn't mention this here, but it's a low divergence.
And the background electrons, like here below, let's say 280 MeV, how do they compare?
When you say the background electron,
so below 280 MeV, so below the peak.
Yeah, you mean in terms of divergence?
No, just how the amount.
Oh, the amount is low. Yeah, is low, and it depends. Typically, it depends on the gradient scale length parameter. So this we saw a dependence on this, and we can. Depending on the gradient scale length parameter, we have a trail of electrons, but usually they are well below the main peak.
I see. Do you use a pre-pulse in these experiments?
Yeah, we have a pre-pulse.
I see. Thank you very much.
Yeah, thank you.
Okay, thank you very, very much, Henry. I think we have to move to the next speaker, Taemong Young. Can you stop sharing?
Hello, can you hear me?
Yes, can you share the screen?
Yeah, I will share my screen. Just a moment. Oops. Yes. Can you see my screen?
Not. Oh, okay, now yes. Okay. Perfect.
Yeah, you can see my screen now.
We see the screen, but it's not full screen. We see.
This is the full screen.
I don't see it.
Maybe some delay. Oh wait. Yeah, Zoom is sharing my window. So can you see my screen?
We see the PowerPoint window, but it is not full screen.
Okay, I don't know how. So let me see. Let me try to do once more.
Yes, we see the next slide, but okay.
Still, I think it's not the full screen. In my computer, it's a full screen.
Okay. No, it's not full screen, but it's okay. So can you go to the first slide then?
Okay. So this is the first slide. No? Is it this first?
I see the second slide.
Really? So in my computer, this is the first slide. What happened?
Okay, now it is. Okay, now it is the first.
Okay. And then, so our stay here. Okay. So some technical problem with the full screen. Anyway. So so we today we had a very nice talk from Sergey and Henry as well.
You when you have 5 minutes left, okay? Because we have 20 minutes in total. I will show you when you.
Yeah, sure, no problem. So then on the relativistic mirror and also its application to the nonlinear the strong field quantum electrodynamics. So here and also as well, I will talk about the relativistic flying mirror and then its application to the strong field quantum electrodynamics. My name is Taemong Jung from LPHYS'23, and then here, as you know, due to the technical advance in the femtosecond high power laser system, we have now the intensity level like 10 to 23 watt per square centimeter. And then this the high power femtosecond laser system usually used in the acceleration of the electrons through the laser gas interaction, and also the acceleration of proton and ions through the laser solid metal interactions. So this is very typical and common nowadays using the high power laser system. The next very interesting thing is to do the laser vacuum interaction. So, but in this case, we need very high field strength, and also the target is different from the others. The usually target is the ultra high intense laser irradiated nonlinear vacuum, and also could be secondary sources, including the high energy electron and also high energy photon as well. So this study can cover the mostly very fundamental science, including the vacuum polarization and also the photon-photon scattering, electron-positron pair generation, etc. So to do this kind of study, so we need a very strong field strength. And then the next question is how to get the very strong field strength. So, okay, so here in this slide, I'm showing you the optical approach to reach the high field strength. And then one way is to using the very short focal length with a fixed laser power. So as you know, the laser field strength or laser power is the inversely proportional to the spot size. And then in this case, by using the very low F number, so we can decrease the spot size and we can increase the field strength. So then what we have to consider is the tight focusing. So if you use the tight focusing, and then in this case, tight focusing means the F number is below 1. And then we cannot use the scalar diffraction theory anymore. And then in this case, we have to consider the vector diffraction theory, and we have to consider the polarization configuration at the focus field. And then, so in the very limiting case of the tight focusing case, it is the Popeye spherical focusing scheme. Popeye spherical focusing scheme means the focal length is pretty much shorter than the beam diameter or the aperture of the focusing optics. In this case, at the focal position, beam is the incidence beam is coming from aerial, which means Popeye direction, and then you can get the theoretical limit for the intensity, laser intensity you can achieve. So that can be described in this way here. And then, so this is the optical approach to enhance the high field, to get the high field strength at the focus. The second thing is to use the relativist charged particles or high energy photons. So if you consider the relativistic electron under the very strong electromagnetic radiation, the electron can be described by the Volkov state like here. And then the radiation power can be described by in this formula. Here the K is the modified Bessel function. And then the parameter U is related to the energy splitting and also the angular distribution. So you can see here very important parameter chi, which is known as the quantum nonlinearity parameters, which is given in this expression. And then, so as you can see here, if you have a relativistic electron and then the electric field strength experienced by the relativistic electron is enhanced by the Lorentz gamma factor of the electrons here. So this is one way also to effectively enhance the field strength with the relativistic particle. And the other one, the last one, maybe is to use the relativistic plasma optics we are talking about in this section right now. So actually the whole concept using the relativistic flying mirror is proposed by Sergei approximately 20 years ago. And then the main idea is to use the reflected source laser pulse from the flying mirror. So when the high intensity laser pulse propagated in the gas medium, so you can immediately generate the plasma cavity, and backside of the plasma cavity can behave as the curved mirror, parabolic mirror. And then if we introduce the counter propagating the source laser pulse, and then the part of it can be reflected and focused to form a very strong field strength. So as Sergei mentioned in his presentation, so by considering the double Doppler shift, the wave number and field strength can be enhanced by P gamma square, and the pulse duration is reduced by P gamma square like this, and then field strength is expressed in this expression here, as Sergei mentioned. So here, as you can see, the geometrical factor, which is determined by the beam size divided by wavelength. Here, this is it's not easy to easily see without any theoretical calculation. So anyway, so focus field strength is enhanced by this way. So here rho is the reflectivity of the plasma mirror. So rho is quite important, has a quite important role to finally determine the final field strength you can achieve with the relativistic flying mirror. So as also we discussed during the right after the Sergei's talk on the recoil effect. Recoil effect is, as we understand right now, it play pretty much important role, because if the source field strength is too high, it can slow down the speed of the relativistic mirror, or even it can break the relativistic mirror. So we have to consider the recoil effect. This recoil effect can be calculated by using the momentum conservation and energy conservation right here. And then we end up with the expression for the frequency change in the relativistic wave in this way. So here in the second term in the parenthesis is related to the recoil effect as well. So this second term tells us the ratio between the energy density of the reflected electromagnetic radiation divided by the energy density of the electron layers. So if we consider very low, this is very low compared to 1, and then we can ignore the recoil effect, which means we have to use the very small laser power in this case, or very small laser intensity, or field strength on the plasma mirror. So, and then also as you can see here, the reflectance is pretty much important. And so in that sense, the reflectance play really important role in the relativistic flying mirror. So we can really consider the reflectance by considering the single electron motion in the relativistic flying mirror. So this is the situation. The plasma medium is moving from the left to the right, and the counter-propagating wave is moving from the right to the left here. But in this case, the normalized vector potential should be pretty much lower than 1. And then the wave equation can be expressed in this way. And then by using the WKB approximation, if electric field strength in the plasma medium can be expressed in this way. And then the electron motion can be described by using the Lorentz equation in this way. And then we can divide this equation into two. One is for the flying motion, the other one is for the oscillatory motion here. But so situation is that the flying motion is pretty much larger than the oscillatory motion. So this equation can be expressed in this way. in the laboratory frame. If we consider this situation in the boosted frame here, boost frame, and then this electron oscillation can be described in this way. And then by putting this expression into the Raynaud-Witcher potential, and then we finally obtain the electric field radiation by the single electron motion in this way. So here the RE is the classical electron radius, but we want to know the electric field by the electron layer or electron medium here. So in this case, we have to consider the coherence. To calculate the coherence, we have to consider the photon formation ranks, and then if we consider the normalized vector potential is pretty much smaller than 1, and then the photon formation ranks is pretty much larger than the Compton wave ranks here, and then in this case, the phase of the emitted photon becomes coherent to the phase of the incidence photon. So we, in order to calculate the electric field reflected by the electron layer or electron medium, we can immediately use the superposition principle to calculate the resultant electric field by the electron distribution by using the integral expression in this way. And then also we further assume the weak reflection limit, which means K kappa square is approximately K square. And then we end up with the expression for the resultant electric field in this way. And then, as you can see here, this is the Fourier transformation. Here is the N is the electron density function. So actually the resultant electric field can be expressed by the Fourier transform of the density function. So then the reflection coefficient, because it is the ratio between the incidence and reflected electric field, is expressed by the in this way in the boosted frame and the laboratory frame here. And then this is the Fourier transform of the density function. So if we consider the very simple electron slab or rectangular electron slab here, we can express it in the rectangular function here, and then we immediately end up with the spherical Bessel function. So the reflection coefficient is expressed in this way with the spherical Bessel function. This is not the this is the ideal case, but in the realistic case, the electron density is somehow expressed by the electron density cost. And then this is the more realistic case. So in this case, we also we want to know the reflection coefficient, and then we have to calculate the Fourier transform of this cost function. Cost function is usually expressed in this way, and then more specifically for the in the laboratory frame. So this is the expression for the density function, and this is the expression for the boost in the boosted frame. And then after some straightforward calculation, we can obtain the reflection coefficient in the boost frame in this way, and also in the laboratory frame in this way. Here the K is also again the modified Bessel function, so which is the exponential decay function. In the wave breaking limit, this modified Bessel function is approximated in this way, and then in that case the reflection coefficient has a finite value as shown here. And then this curve shows us the reflection coefficient depending on the sharpness parameter. Here, the sharpness parameter is how close to the wave, tells us how close to the wave breaking limit. So actually, the 0 is almost like a wave breaking limit. So as you can see here, the reflection coefficient is pretty much dependent on the sharpness parameter, and also when the electron density cost getting narrow, the reflection coefficient is like 10 to minus 3 level. This is the calculation parameter I use, and then I also calculate at different electron density, maximum electron density of the gas. And also, the one of the fundamental interests is to calculate the field structure and the peak field strength. So if you consider the
sorry to interrupt you. You have 4 minutes. 4 minutes. Okay.
I have yes. So this is the flying mirror in the laboratory prime, but if we transform into the boosted prime, the focal length is getting pretty much short. In this case, we can apply the Popeye spherical focusing scheme, and then this is the expression for the electric and magnetic field for the radially polarized polarization. So because the radial polarization has the analytical solution, we use this radial polarization, and then this is the field strength we can obtain. And then this is the analytical result based on, we calculate based on the previous equation. This is the numerical result Sergey already showed us. And then you can see the similarity. And then, yes, because and also we have the reflection coefficient, formula for the reflection coefficient here. And also we have the expression for the peak intensity. By multiplying these two, we can calculate how high intensity we can achieve here. And then it also strongly depends on the sharpness parameter for the electron curve case. And then the main message here by almost in the wave breaking limit, the maximum intensity, peak intensity we can obtain is like 10 to 27 watt per square centimeter here. This is also the calculation parameter I used. And then I consider the 4 petawatt, and then the field strength for the driver pulse is 2. And then because we can obtain very high field strength, one of the example I can think about for the study on the strong field QED is this. So we can collide this high field strength to the high energy gamma photon. High energy gamma photon can be generated from the radio solid matter interaction. And the underlying physics of this, the high energy gamma photon generation is multi-photon compton generation during the radio solid matter interaction. And then, so by shining this one to this very strong field region, we can consider the somehow electron-positron pair generation through the multi-photon, the Bright-Wheeler process. We, in the last few years, we focus on the high energy photon generation in the radio solid matter interaction. This is, you can find some interesting result from our publication here. So yeah, something like this. And then, because time is limited, I will not go to the detail on these two slides. And then actually, so we can consider this previous scheme, and then we can calculate the quantum nonlinearity parameters. So this is the quantum nonlinearity parameter with high energy gamma photon here. So, and also this is the calculation result depending on with respect to the sharpness parameter again, and also as you can see here, the quantum nonlinear parameter pretty much go over in the wave breaking limit, and then pretty much go over 100. So this is also very interesting topic. As Henry mentioned, the relativistic flying mirror is not anymore the scientific fiction, and maybe also can flourish very interesting fundamental physics. And then, so this is the end, the conclusion. So I discussed the field enhancements using the relativistic flying mirror, and also the relativistic flying mirror can be used to study on the strong field quantum electrodynamics. Okay, this is the end.
Thank you very much. We are unfortunately a bit late, so there is time for a quick question. If you have questions, please raise your hands. Okay, then we'll ask one quick question. So these limits that you're showing are theoretical, right? So upper limit.
Yeah.
Okay.
This is the theoretical calculation.
Okay. Did you check with simulations how well they perform in a more realistic?
Oh, not yet, but we have a plan.
Okay. 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 Then thank you. I think we unfortunately have to move to the next speaker.
Yeah.
Yeah. Can you stop sharing the screen?
Sure.
Thank you. Next speaker is Alexander Samsonov. So
yes, hello.
The screen, please.
Yep. Can you hear me well?
Yes, we can hear you. We see the screen. So, okay. So, next speaker is Alexander Samsonov. He will talk about electron motion and relativistically strong plane waves. So, you have 20 minutes. I will show you this like this when you have 5 minutes to the end. Okay. Thank you.
Yeah, good. Okay. So, hello, everyone. First of all, thanks to organizers for providing a great opportunity to share results of our research. So my name is Alexander Samsonov, and I'd like to talk about electron motion in relativistically strong plane waves, mostly focusing on effects of radiation reaction. Now, it's been known for more than a century that electron experiences a recoil force from its own radiation when moving in external fields. And this effect is usually considered negligibly small for relatively weak fields, but for stronger fields, which are characterized by dimensionless field amplitude A naught exceeding unity, it is known that radiation reaction can drastically change electron dynamics. And there are various effects caused by radiation reaction in strong fields during, for example, laser plasma interaction. They include, for example, alteration of particle acceleration mechanisms, effective absorption of laser radiation, inverse Faraday effect, radiative trapping of particles, and many others. Now, in order to include this effect for ultra-relativistic particles, one usually adds an additional term to the motion equations. And in regime of weaker fields where radiation reaction is negligible, one can roughly estimate that the characteristic scale of the electron energy in external field is of the order of the dimensionless field amplitude. But when we want to consider the case where radiation reaction significantly changes electron dynamics, it's useful to introduce so-called strongly radiation-dominated regime, which is basically realized when electron, due to abundant radiation, is unable to gain the same level of energy, meaning that the following inequality is satisfied. And it's been shown by several research groups, including ours, that in this regime, electron dynamics can be greatly simplified, and electron trajectories attract to so-called asymptotic or radiation-free trajectories, which are described by the following simplified equations. And moving along this asymptotic trajectory, electron basically does not experience any radiation friction. And quite surprisingly, the same behavior was reported in multiple astrophysical environments quite a long time ago. Now, one of the major drawbacks of this approach is that in many field configurations, these equations simplify the problem so much that no useful information can actually be gained from solving these equations. In that case, it's more practical to develop a sort of perturbation theory, assuming that electron velocity is not exactly coincident with this radiation-free direction, but slightly deviates from that. And this procedure of perturbation theory can be carried out in general case for arbitrary field configuration, and we can obtain the following simplified motion equations, where terms like F1 and chi can be explicitly written as expansion series in a small parameter of this problem, which is noted as delta here. Yeah, at first sight, it might seem that these equations are more cumbersome and more difficult to solve. But as it turns out, in multiple configurations, these equations can be actually solved explicitly. And some of these solutions you can find in our recent paper. And yeah, in the same configurations, non-reduced motion equations usually cannot be solved explicitly. And in this talk, I want to demonstrate you how the same approach can be applied to a problem of electron motion in plane waves with account of radiation reaction. Now, first of all, let's define the field properly define the field configuration that we will consider. So here is the configuration. So the fields, electric and magnetic fields, only depend on the phase phi, which is t minus x. And we also only consider situations where electric and magnetic components are equal and perpendicular to each other. Now, if we applied this sort of zeroth order radiation-free approach, it yields that asymptotically electron velocity aligns with Poynting vector, and the amplitude of the velocity reaches speed of light. And yeah, as I told, it's not a particularly useful piece of information because we essentially lose any information about the details of the electron motion when it approaches this asymptotic. So in that case, it's very useful to apply this perturbation theory and write the simplified motion equations, which you can see on this slide. And as it turns out, solving these equations is actually a matter of choosing a right set of variables. So first we introduce magnitude of transverse momentum P, and we also switch to phase phi as our integration variables. And then from these equations, it follows that there is integral of motion if we artificially neglect radiation reaction. And this integral of motion is nothing else than so-called Lightford momentum, which is the difference between the energy and longitudinal momentum. And this integral of motion is a well-known thing in this problem of electron motion in plane wave. But if we actually account radiation reaction, it turns out that equation for this Lightford momentum actually decouples from other equations, and we can solve it independently. And the solution to that equation is very simple. Here you can see that. And here I introduced the dimensionless and also Lorentz invariant parameter A, which basically controls how strong radiation reaction is. And the large phi is basically the integral of the intensity of the plane wave over the phase phi. Now, after we obtain the solution for Lightford momentum, the motion equations for transverse components of electron momentum are greatly simplified, and they can actually be written in a form of this linear system of equations if we introduce some intermediary variables epsilon and beta. And after we solve this system of equations, we can finally find electron energy and longitudinal momentum by using this algebraic expression. So on this slide, we essentially have the final solution to this problem of electron motion in plane wave with account of radiation reaction. And I think that there is even a general solution to this simple system, but I'll just consider a couple of special cases where the solution is even more simple. So the first special case is linearly polarized monochromatic plane wave. And here you can see the solution that we get from the previous slides. And it's written in a really compact form. It's easy to analyze. And here I need to stress that technically this is not an exact solution, because it's obtained from a perturbation theory. So this is not the same as exact solution obtained by Antonini di Piazza in 2008, I guess it was. But still, if we compare this solution to numerical solution of non-reduced motion equations, which is shown on this graphs, we can see that these solutions basically coincide exactly. And before actually analyzing these results, I will present the second special case, which is a circularly polarized monochromatic plane wave. In that case, the solutions for transverse momentum are even simpler. And so yeah, now how this solution is different from a usual solution without radiation reaction. Now, the most interesting and quite unexpected thing is that when we account for radiation reaction, electron is actually able to gain unlimited energy in plane wave, which you can see from the left graph. At the same time, the parameter chi, which governs QED processes, increases to 0. So the radiation of the electron becomes sort of more and more classical. And another not so evident thing is that if we calculate the total energy radiated by the electron while it moves in plane wave, it turns out that this amount is actually finite. So despite the fact that the plane wave is able to accelerate the electron up to unlimited energy, the energy radiated back by the electron is a finite amount. So also from this solution, it might appear that plane wave is not an optimal configuration for observing QED cascades, because chi parameter of electron increases, and it's generally believed that for self-sustained QED cascade, at least, you need that so that chi parameter increases during the particle motion in electromagnetic field. But let me discuss QED cascades and plane wave in more detail, because it turns out it's not so simple. So on this slide, I showed the results of simulation, particle and cell simulation, where a bunch of gamma photons counterpropagate an intensive laser pulse. So in this configuration, obviously, of counterpropagating bunches, we expect a QED cascade, but a shower type cascade. And indeed, if we run the simulation, we can see that there is a small portion of electrons and positrons being formed, but after some time, the QED parameter chi decreases, and because of that, the QED cascade stops, and the number of secondary particles does not increase. But what's important in this simulation is that the field of the laser pulse is fixed, so it does not respond to any currents occurring in this electron-positron plasma. And this becomes very important, because in this simulation we have the same initial conditions, but this time it's a proper particle and cell simulations where currents of electrons and positrons contribute to electromagnetic field. And if you look at this simulation, it's actually quite drastically different. So we can see that chi parameter on this middle graph stays high during the simulation and never actually drops. And the electron-positron plasma actually is being formed, and it propagates towards the laser radiation and efficiently absorbs it. So comparing this to the previous simulation, we can definitely say that this is a self-sustained QED cascade, because the seed is no longer participating in this process. And next, I try to briefly explain why this cascade is possible. Counter to our sort of intuition that the chi parameter actually decreases in plane wave. Now, the main thing is that If we take a look at the field configuration inside this dense pair plasma, it turns out that magnetic component of the plane wave is actually larger than the electric one, and the angle between the electric and magnetic component is a bit larger than pi/2. So we have the configuration, which is basically not the same as we considered in first part of our talk, and we cannot directly apply the results of the solution which I presented. But in order to understand how particles move in this configuration, first we can notice that there is an auxiliary reference frame moving along the x direction, which is the direction of the laser pulse propagation. And in this reference frame, electric and magnetic fields are anti-parallel. And in that case, the sort of average electron motion is also anti-parallel to the electric field. But since there's also a magnetic field, the particles also revolve around that magnetic field. And in order to confirm that, we can see at the trajectories of individual particles in our simulation inside this dense plasma. And indeed, we can see that, we can see that they revolve around this magnetic field. And this is a very important feature because occasionally such electrons can emit a hard photon which propagates towards laser radiation, and it can reach a sort of vacuum region where laser field is not depleted, and with high probability it can decay into electron-positron pair. And this pair, being born basically in vacuum, is moving as I described in the first part of the talk. So it's quickly accelerated in longitudinal direction, and it gets back to the dense plasma region where trajectory changes qualitatively, and electrons start to move along these helical lines and occasionally emit gamma photons towards the laser radiation. And this is how this process is able to repeat and sustain itself. And here you can also see a little cartoon where this process is shown in dynamics. So in terms of QED parameter chi, it actually increases where both electrons cross this interface between the vacuum and plasma region, and also for gamma quanta, because when they propagate from dense plasma region, their laser field is depleted, and in vacuum region, laser pulse is really strong. And based on this qualitative understanding of how this process works, we developed a semi-analytical model a couple of years ago. And I won't dig into details of how this model works, but what I will show you is how this model compares to results of full 3D peak simulations. So on the top, you see the solution of our model equations, and on the bottom, results of full peak simulations. And you can see that they agree quite nicely, which sort of says that indeed our understanding of this process and the mechanism of QED cascade and plane wave is relevant, and we understand that. And a final note, you might argue that in the simulations that I showed previously, it's not a purely A-type cascade, a self-sustained cascade, because initially we have an energetic seed. And but from these simulations, we can see that the same type of cascade is able to develop when we have initially a stationary target in form of, for example, a very thin foil. And in that case, with sufficiently large intensity and density of the seed, this cascade is able to develop. So let me conclude. So I showed a general approach which can be used to simplify motion equations in a strong radiation-dominated regime. I then applied this approach to find an approximate solution to the problem of electron motion in plane wave with a counter radiation reaction. And I discussed several interesting features, such as unlimited longitudinal acceleration and finite radiated energy. And finally, I explained how a self-sustained QED cascade can actually develop in plane wave. So that's it from me. Thanks for attention. And I hope you have some time for questions.
Thank you very much. Thank you very much for a nice talk. It's now time for questions. If you have questions, please raise your hand. Okay, I think I will start first. So for this plane wave, the main problem that I can see is that in reality you have focused pulses. Did you try to compare and see how big it should be the focusing of the pulse to have to work?
Yeah. So basically, what we can say is that for focused laser pulses, the sort of interaction time is limited by Rayleigh length. So in fact, you can calculate. So these graphs which are plotted against the phase phi. But in laboratory frame, if we calculate the solution as functions of t of time, then we can basically from this solution calculate how many oscillations you will have in your focus pulse, and we can calculate the sort of this net energy transfer. So it won't be unlimited, obviously, but still, for quite long pulses, I guess that you can see some features of the solution.
I would expect that particles are emitted at large angles, so it's not just the Rayleigh length. So it's really because they spread transversely.
Yeah, but in fact, this radiation reaction stops them from being emitted at large angles because radiation reaction actually decreases the transverse velocity and transverse oscillations. Mm-hmm. So it traps the particles in a region of stronger field.
Okay, but this makes also important the size of the
yeah,
spot.
Sure.
Okay, we have one question from Laszlo. Please go ahead.
Yeah, it's really interesting to see such a basic science and connected to radiation reaction. But could you interpret this result? I mean, in without radiation reaction, what happens? The electron starts to get accelerated, but the laser field is faster, in the plane wave is faster, and then it gets into dephasing regime, and it loses its energy. Why does here the electron not loses the energy? I don't see this.
Yeah, so the idea is that the accelerating and decelerating phases become non-symmetrical because of this radiation reaction. And how to explain that? So, yeah, you can understand it in terms of this chi parameter, which is basically proportional to this light front momentum. And because it increases, the difference between the energy and longitudinal momentum decreases. And that's why you get sort of unlimited acceleration. So radiation reaction breaks the symmetry between accelerating and decelerating phases. So then there is a net acceleration if you integrate over a single period. It's not really obvious, but it is how it is.
From what you would estimate, from which A naught is it relevant? Here you calculated 500.
Yeah, so this is for 500, but actually this solution is applicable for any A naughts larger than unity. So the sort of this the slope of this growth of the energy is basically controlled by this parameter. So as you can see, it depends on initial value of chi parameter and A naught. So obviously and chi at the same time also depends on the intensity of the plane wave. So for lower intensities, this increase of energy will happen in many periods.
Effectively, it means that the Lawson-Woodward criterion is not valid, or theorem is not valid.
What again, sorry?
The Lawson-Woodward theorem is not valid.
Yeah, because the conditions of the theorem are broken in this regime, because we can't say that electron penetrates the laser pulse moving along the straight line.
Mm-hmm. I see. Thank you.
Okay, thank you. I think it's time to close this session because in 7 minutes the next session will start. So we take the chance to thank all the speakers. There were many discussions, many interesting questions. So we went a bit above actually the limit. So we see in 7 minutes. Okay. Thank you all. Bye.
Bye-bye.